Yabagi Bayaw. Today, I'm going to show how to solve a problem in Thermodynamics, Chapter 6, Gas Cycle. So this is my problem. You can see this problem from the book of Yunus, say single, page 540, problem 9-46. An air standard diesel cycle has a compression ratio of 16 and a cutoff ratio of 2. At the beginning of the compression process, air is at 95 kilopascal and 27 Celsius degree. Accounting for the variation of specific heats with the temperature, determine the temperature after heat addition process and the thermal efficiency and the mean effective pressure. So this is my figure. So this is the table. This table came from as a unit, property as a unit, table A-2. Since we are talking about air standard, so this is the givens. Our constant pressure is 1.005 kilojoule per kilogram times Kelvin, and constant volume is 0.718 kilojoule per kilogram times Kelvin. Our gas constant air is 0.2870 kilopascal times cubic meter per kilogram times Kelvin, and the K is 1.4 and the pressure is 95 kilopascal. Compression ratio is equal to volume 1 over volume 2, which is 16. And volume 3 is constant with 2, that is cutoff ratio, which is equal to 2. So the requirement is T sub 2, thermal efficiency, and the MEP, which is mean effective pressure. First, we're going to find process 1-2 isentropic compression. So this is the equation, which is T sub 2 is equal to T sub 1. Like what I said, V sub 1 is V over V sub 2 is equal to compression ratio powered K minus 1. So our temperature, which is 27 Celsius plus 273, so 300 Kelvin times 16 power of 1.4 minus 1, so our temperature 2 is 909.4 Kelvin. Then after that, we proceed to process 2-3, which is pressure is constant heat addition. The equation that we're going to use is P sub 1 times T sub 1 over V sub 1 is equal to P sub 2 times T sub 2 over V sub 2. Since pressure is constant, we're going to cancel it. So this is the equation that we're going to use. T sub 3 is equal to T sub 2 over V sub 3 times V sub 3 over V sub 2. The V sub 3 is over V sub 2 is equal to 2. So this is the equation that we're going to use is 2 times T sub 2. So 2 times 909.4. Our T sub 3 is equal to 1818.8 Kelvin. Then after that, we're going to find the specific heat in, which is equal to H sub 2 minus H sub 1. H is enthalpy. So the other equation is constant pressure times T sub 3 minus T sub 2. So our constant pressure is 1.005 kilojoule per kilogram times Kelvin. So times the temperature 3, which is 1818.8 minus 909.4 Kelvin. Our specific heat in or Q in is 913.9 kilojoule per kilogram. Then proceed to process 3-4 isentropic expansion. The equation that we're going to use is T sub 4 is equal to T sub 3 times V sub 3 over V sub 4 power of K minus 1. So V sub 3 is constant with the V sub 2, which is 2, and V sub 4 is constant with the compression ratio, which is 16. So our T sub 3 is 1818.8 Kelvin times 2 over 16 power of 1.4 minus 1. Our temperature 4 is 791.7 Kelvin. Then we proceed to process 4-1. Volume is constant heat rejection. The equation that we're going to use is specific heat out is equal to U, which is in specific internal energy, which is U sub 2 minus U sub 1 is equal to constant volume times temperature 4 minus temperature 1. So our constant volume is 0.718 kilojoule per kilogram times Kelvin. times the temperature, 791.7 minus 300 Kelvin. We're going to cancel the unit Kelvin. And our specific heat out is 353 kilojoule time over kilogram. So next is we're going to find the thermal efficiency, which is the equation is thermal efficiency is equal to 1 minus Q out over Q in, and our Q out is 353 kilojoule per kilogram over 913.9 kilojoule per kilogram. Our thermal efficiency is 61.4%. Then after that, we're going to find the MEP or mean effective pressures. But first, we're going to find the work net out. Work net out is equal to Q in minus Q out, which is 913.9 kilojoule per kilogram minus 353 kilojoule per kilogram. Our work net out is 560.9 kilojoule per kilogram. Then after that, we're going to find the volume sub 1 or volume maximum. The equation that we're going to use is volume sub 1 is equal to gas constant R T times T sub 1 over P sub 1. So our gas constant, which is 0.287 kilopascal times cubic meter per kilogram times Kelvin times the temperature 1, which is 300 Kelvin over 95 kilopascal. So we're going to cancel the kilopascal and Kelvin. So the V sub 1 is 0.906 cubic meter per kilogram. Then after that, we're going to find the equation for V sub 2. The equation for V sub 2 is equal to V max over R, which is R is compression ratio. So the equation for MEP or mean effective pressure is equal to work net out over volume sub 1 minus volume sub 2. So volume net out over volume sub 1 times 1 minus 1 over R. So our work net is 560.9 kilojoule per kilogram over volume sub 1, which is 0.906 cubic meter per kilogram times 1 minus 1 over R, which is 16. We're going to times 2 kilopascal per cubic meter over kilojoule. We're going to cancel the kilojoule and cubic meter. Our MEP or mean effective pressure is 660.4 kilopascal. Thank you for listening and have a great day, everyone.